Yeah, thank you, Rajesh. We are recording now. And good morning to all of you. Welcome to the second of my 4-lecture series on the subject of the interaction between complex analysis and linear algebra. To people in the audience, can anyone just jump in and say that not Rajesh, who I am able to communicate with, anyone else in the audience, am I audible to you? Am I clear to you?
Yes.
Yes.
Okay.
Yes.
All right,
Yes,
fantastic. Very good, thank you very much. So before I begin the proceedings today, I just wanted to tell you that this mode of lecturing, I don't know how familiar it is to you, which is basically, I'm just doing stuff on the blackboard. This is as close to a conventional class that one can get to in the online mode. However, I did tell you during the tutorial that I will put together some handwritten notes based on my lecture and put them up in the Dropbox folder. I have done that, and in fact, the agreement will be that on the night of a day that I have lectured, some lecture material will come up. If I am using the Blackboard, then there will be handwritten notes to supplement the lecture. In at least one of the lectures, I might find it more convenient to use slides, and in that event, you will have slides. For those of you who, I know some people who were trying to access Dropbox through their mobiles were having some difficulty seeing the relevant document. So let me, in fact, give the Dropbox link to the PDF document, which is essentially a scan of a set of handwritten notes. I have put this in the chat, okay? So with those words, let me proceed with today's business. But then before I do, I want to remind you of the last thing that we did, because the last thing that we did is actually going to be the transition to the next theme in this set of 3 themes that I said that my talks would be based on. So please recall the last let's say concept, C, in lecture 1 was the map. I had used this notation, I believe, bold J, sub D. This is a real linear map from R 2D to itself. And it has the following effect. It takes a vector which I am going to label as x1, y1, dot, 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 xn, yn. So, I don't know why I wrote n. My domain vector space is R2D, so I should say xd, yd. And remember, a general point in the 2D dimensional Cartesian product of R with itself looks like this, but there is a purpose for the labels that I used. You'll remember the purpose more clearly from what we did in the first talk. So this map, this J map, what it does is, so this map J sub D carries this vector to the vector minus y1, x1, comma, the next pair of entries would be minus y2x2 and so on, minus y dxt. So, so this map satisfies and I had the occasion to mention this relation in the tutorial. JD squared, that is JD applied to itself twice, is actually negative of the identity transformation on R2D. So what I want to do is I made the statement in the tutorial, but I don't know how many people attended the tutorial. So before I proceed, I want to say that an R linear transformation, so more generally, an R linear transformation, let's call it J. Now I'm writing this J differently to indicate I'm not just talking about this object anymore. J from V to itself, V an R linear space satisfying the above identity is called an almost complex structure. This is called an almost complex structure. So the substantively new theme in today's lecture is going to be some theory about almost complex structures. However, the technique that we saw in the previous talk, it has another application which is kind of important in complex analysis. And this time we will stick to complex analysis in one variable. In what we discussed in the previous lecture, you will appreciate that to state the main theorem in the previous lecture and state a non-trivial version, sort of the non-trivial or the general version of the theorem that we discussed in lecture 1, my motivation for it, and it's actually really the key motivation for that theorem, I had to talk about holomorphic functions in several variables. Today, and for the remainder of my talks, if at all I'm talking about complex analysis in connection with linear algebra, I will always be talking about functions that are familiar to the vast majority of you, which is functions in one complex variable. So what I want to do is another topic, analogous to the discussion on the 11th. So in the interests of continuity, because some of the things that we did in detail in the tutorial is probably fresh in your mind right now and might not be fresh later on, let's leave this stuff here for the moment and transition to this another topic I'm telling you about, and I'm going to begin with a definition. You've probably heard this word earlier, but this is the term conformality. But let's write it out. Let omega be an open subset of C, and F a map or a function, whatever you want to call it, from omega into the complex plane. We say that F is conformal if F preserves angles at each point in omega. Okay. So the question arises, okay, what do we mean by preserves angles? Now, an angle is a purely geometrical notion, but it is not sort of the, let's say, most elementary of notions in geometry, and it's certainly not the most elementary of notions in linear algebra. Since this is an AIS on linear algebra, you would probably be able to intuit that if I want to talk about preservation of angles, I somehow need two vectors. And I want to be able somehow to conceptually talk about the angle between a pair of non-zero vectors. Fortunately, there is a structure that one can augment a vector space with, which allows us to talk about angles. Does anyone remember what that structure is? If we enrich a vector space with an additional structure, we can talk about angles. Do you know what that structure is? Can anyone tell me?
So inner product.
Exactly. So we need to talk about inner products. So everyone kind of knows this. However, the modern definition of angle preservation simply makes a reference to the real tangent bundle of omega. Then on every fiber of the real tangent bundle, the total derivative of f, if f were differentiable, the total derivative of f is a linear transformation, and angle preservation can be stated in terms of some general property of that linear transformation. So in a lot of modern textbooks, conformality is defined exactly in this language, but it is actually instructive to try to understand formally what the tangent bundle is as a thing. Where does it come from? So I'm not going to do that. This is not a lecture on manifold theory. But what I'm going to do to describe angle preservation using sort of a hands-on approach is at the bottom one of the ways in which the tangent bundle on any manifold is formalized. I will probably not use the word tangent bundle any further going forward, because as I want to say, I want to get to the guts of what we mean by preserves angles. And today's discussion is for us to discover the definition of conformality in terms of the total derivative of this f. But I want to go a little further than that as well. So let's carry on with that. I think people will have made a note of what's on the board, but let me just take a few seconds before I erase this. All right. Did someone say something to me?
Sure, sir. Sure, sure.
Okay, thank you. Okay, so let's discuss what we mean by preservation of angle. So the question is, so what does preserves angles mean? So there is this question, and let's discover the answer. So when we actually put our hands on the issue of conformality, that's where the linear algebra comes in. For the next somewhere between 5 to 10 minutes, I'm going to focus on geometry, but this is easy geometry. This is geometry on the plane, on the surface of the blackboard. So classically, it means the following. But let me, in fact, formally acknowledge that you will see textbooks today where the definition is given in terms of total derivatives. Okay, so this can be expressed in the language of, so remember I said F is a complex valued map at the beginning of this discussion, but we know that underlying every complex valued map is a real map, that is a R2 valued map, a real vector space valued map, and its classical total derivative, we use this notation, right? df sum r. So classically it means the following, and then this can be expressed purely in the language of this object, right? But the following justification or the following explanation is the basis of how this definition purely in terms of the total derivative is arrived at. So the following explanation is the basis of the definition seen in modern texts, seen in very recent texts. And then once again, the advantage of what we wind up with turns out to be generalizable to higher dimensions. So most people in this audience would have heard of conformal mappings in the context of mappings from a planar domain into the complex plane. But in fact, conformality can be expressed in higher dimensions as well, in all real dimensions. And And the reason is because the idea of angle preservation is not peculiar to mappings from a planar domain into R2. That's one. And more than that, when we get to the linear algebraic phrasing of conformality, then that linear algebraic phrasing generalizes to arbitrary dimensions. It would, I must actually say, it would not be a purely linear algebraic phrasing. It would be an inner product phrasing. Okay, so to carry on. So it means the following. What does it mean? So it means the following. So at each Z in C, so the answer to this requires a couple of steps. So at each Z in C, consider two smooth curves. So in fact, so when you see the word smooth, a lot of people would start imagining C infinity smooth curves. We don't need that. We just need to C1 smooth curves. Say capital C1 and capital C2 passing through Z. So the picture here would be sort of like this. So this coordinate axis that I drew is a representation of R2. Let me get some colored chalk. Where is it? Okay, so what I mean is, so this here is a curve C1, and then let's draw another one. This here is C2. Okay, so I should actually have said, you'll see in a moment, I should have said consider two directed sorry about this, two directed smooth curves, meaning to say I also want to put arrows on them, right? So remember, so these are curves passing through a point Z in C. So you'll see in a moment why I want directed curves. So what does this mean? This means that there exists some epsilon positive and maps gamma 1 and gamma 2. These are maps from minus epsilon to epsilon into C, such that these gamma are parametrizations of C1 and C2. So as we move in time, we identify a direction of traversal, and we need that, and that's why we need directed curves. So such that gamma sub j is equal to C, gamma sub j of minus epsilon to epsilon is the curve Cj. I'm going to say that at 0 is the instant in time when we hit the point Z. And now this is the crucial thing. So you see, I want directed smooth curves. So I don't just want this parametrization to be C1. So let's write this. So gamma 1 and gamma 2 are of class C1. But I don't just want them to be of class C1. I want, you see, C1 and C2 shouldn't have any corners, any angles. And so as you know that this is given by the condition, gamma sub j prime of t is non-vanishing for all t, which is just a way of saying there is a definitive tangent vector at every point of this curve. So let's now draw these tangent vectors, right? So for C1, this line that I'm just drawing is the tangent vector. So I'm going to have to remove this Z. I'm going to have to move it a little bit out of the way. So this ray that I drew is the tangent vector to the curve C1. And then this other ray that I just drew, is the tangent vector to this other directed curve, right? The curve C2. So the angle between these is so typically we measure angles in the counterclockwise direction. So this angular traversal is schematically the angle we are talking about, okay? But then how do we express this? How do we express this quantitatively, right? So for that, we need to do the following, right? So what I'm going to do now is I want to be able to, I hope this condition is clear. This gives us a well-designated tangent vector. So now what we do is this. At Z, fix some ray. That's R for ray. So let's write this script R sub Z as my symbol for a ray. Fix some ray R sub Z originating at Z. And let us write. So I'm going to come back to these curves in a moment. So let us first write the following. So all of you have heard of an argument in the context of complex analysis, right? And most of you are aware that an argument is not well defined. We need to be sort of careful when we use the term, which is why I describe this ray. So I am going to describe the argument with respect to this ray of V. So this V is a vector, a non-zero vector. So let's see what this is. So the argument is defined as simply the angle. But then, as I said, when we talk about the argument, we need to be careful because if I measure this angle, any integer multiple of 2 pi n plus this measurement could validly be an angle. So I need to capture what is being said in this picture very carefully. So this is the angle lying in the interval that is closed in 0, but is open at 2 pi. so that the ambiguity is resolved. So this is the angle lying in here between RZ. So I'm not going to draw this RZ in the picture, or what the hell, maybe I will. Why don't I do that? So I'm rapidly running out of colors that are easily readable in the blackboard, on a blackboard. Let's say this dotted line that I'm drawing. In 2 minutes, I will have explained that the choice of this ray is completely irrelevant to the discussion going forward. So this dotted line that I have drawn, let's say for our present purposes, this is the ray R sub Z. So this thing is the angle, and I require my angle to lie in this interval between R sub Z and V measured counterclockwise. So CCW means counterclockwise, meaning this way. Okay, and then I need to tell you where V. Now you see, in these sorts of discussions, when we talk about V, we are talking about the vector V in the context of geometry, which means that in this sort of a picture, this V is actually an element sitting in the space of all tangents at the point Z. So those of you who've done some very introductory differential geometry will know that what I mean is all V in the tangent space at the point Z of where I need the duster, yes, tangent space of R2. And to be faithful to this picture, because we cannot talk about an angle between a zero vector and a ray, so my vectors are in T sub Z of R2 minus 0. Okay, so this is what I mean by argument, and I'm now all set to give the definition of the angle between C1 and C2. Okay, so I'm going to keep the picture up, but I am going to erase all of everything except maybe this definition down here. So let me first, okay, so let's erase.
Sir, could you please explain where is this vector V coming from?
This is transitory. I want to first be able to define what I mean the argument of a vector.
Okay.
But in answering the question that I posed, you see two vectors over here, right? Do you see this vector here and this vector here? These are the tangent vectors to C1 and C2 respectively. Do you see them?
Yeah.
So this is transitory. So in mathematics, we like to first make a general definition and then apply the definition, right? So does that kind of answer your question?
Yes, sir.
So what I'm going to do is, so setting aside the question of where this vector comes from, do you at least understand this definition?
Yes, sir.
Yes. So this is auxiliary. This is a way of saying for any vector that is non-zero, I can define this as I have written on the RHS, okay?
Excuse me, sir.
Yes.
What is that W?
This one?
Yeah.
It's actually, I mentioned this, right? CCW
Yes, CCW.
is my short form for counterclockwise.
Okay. Thank you.
Okay, so this board now, I will have to get rid of this dust. If I were lecturing in person, this is not going to trouble anybody. But since Zoom videos are necessarily a little grainy, I need to get rid of this dust that is building up. Okay, I think this is good. So I'm going to preserve this definition for just a couple of minutes more. So I have this. Now I'm in a position to define then, you see, the angle between C1 and C2. Well, it is what we see over here. And you see, what happens is when C1 and C2 intersect at the point Z, they kind of make an angle between them, right? But how do we conceptualize the angle when we say, yeah, I see an angle between them? What we actually see is the angle between these vectors. These are the tangent vectors. And what are the tangent vectors? They are respectively. So this orange thing is C2. So this is gamma 2 prime at 0. And then this is the tangent vector. Oh, sorry. I call both of these C2. I don't know why I did that. One of them has to be C1. Let's call this C1s. So you didn't point out to you that I call both the curves C2. So this orange guy is C1. So this tangent vector is nothing but gamma dash sub 1 at 0. And this is gamma dash 2 at 0. So therefore, when we talk about the angle between C1 and C2, what we really mean is the angle between gamma 1 dash 0 and gamma 2 dash 0. And then this. Now, I have discussed what we mean by the angle with respect to some reference direction, which I'm calling R sub z, and a given vector, right? So you see, if I want to measure this angle, so if I want to measure this angle, then what I will be writing is, so I'm writing the angle between gamma 1 and gamma 2. So gamma 1 is coming first. So this orientation is temporarily going to be important. So since I have marked the arrow this way, I actually, since I want to measure the angle between gamma 1 comes first. This is the tangent vector to gamma 1. So let's make this correction to indicate that I'm going from this vector to this vector. So my angles are allowed to be positive or negative because measurement in the counterclockwise direction is, you see this here? This is going to give us a positive number. It's going to go up to 2 pi, but it's not allowed to be 2 pi or larger. So if I want to preserve this orientation that gamma 1 comes first and gamma 2 comes second, then this is in fact simply going to be the argument ARG R sub z, comma, gamma 2 prime at 0. minus ARG R sub Z, comma, gamma 1 prime and 0. So the person who asked me, where is this V coming from? Do you see V is my variable for which, for this picture, I'm substituting gamma 2 prime and gamma 1 prime respectively. So what I'm doing is basically this. I have a reference direction. And let's look at this. So what I'm doing is I am measuring this angle. I'm measuring this angle. And the direction in which I'm moving my fingers indicates the counterclockwise direction. And then I'm going minus. My reference direction remains the same, but I'm now measuring this angle, which you can see is much bigger. So as you can see, this difference would be negative. The negative indicates, in fact, what this arrow was telling me. This arrow, if I go from gamma 1 prime to gamma 2 prime, this arrow must be drawn clockwise, which is the negative of the counterclockwise direction. So this is all good. This difference is motivated by what my geometry wants to capture. And I want to just make one final assertion. Note that since the RHS is a difference, RHS is a difference, the choice of this reference ray R sub Z doesn't matter. Right? So this reference ray was only there to write things quantitatively. But I hope you realize that if I had taken a different reference direction, what we should expect, which is the way to measure this angle, and that you should expect that number to be negative, doesn't change. And that is because of this being a difference. So this is something fairly standard in complex analysis when we want to talk about arguments. So if you just want to talk about arguments, then life is difficult. We need to talk about a branch of an argument. But when we have differences, suddenly things become very simple. Okay, so now having done this, so this is only the description of what we mean by an angle between C1 and C2. I still haven't told you what we mean by preservation of angles, right? So now I want to talk about, so now in my definition, I had put no condition on F, but now I'm going to demand that F from omega to C is of class C1, okay? So we understand that we are talking about the class C1 classically. So we are identifying the complex plane with R2. So we want this now. So we say that F preserves angles. Preserves angles at Z. So this is the term I'm defining. So what is this Z? Now Z has to lie in the domain of F. So Z is now in omega. If two things happen. You see, first of all, I want to let me write down the second part of this condition first. And then what I'm writing will motivate why I need the first condition. But logically, I would have to stipulate the first condition before I can talk about the second condition. So bear with me. Can I erase this definition now?
Yes, sir. Yes.
Right, thank you. So I need more
Sir,
space.
excuse me, in that,
Yes.
can you please say what is that t squared of r?
R,
T2 of r.
not T2 of R. It is T sub Z of
Oh, it's
R2.
z. Okay, okay.
Yes.
Sorry, it's not clear.
You are familiar with the tangent bundle, right?
Not that much.
But you've heard the term, right?
Yeah.
So then if you are not familiar with the tangent bundle, just take T sub Z at R2 to be my short form for the set of all vectors whose origin is not the global origin of coordinates, but is a point set, meaning it captures this picture. Is that understandable?
Yeah, yeah, yes, sir. Yeah.
Good.
So why can't we take a vector v to be 0? As in we excluded that point, right?
Well, how would you measure I mean, this picture wouldn't make sense, right? How would you measure the angle between a zero vector?
Okay. Understood.
So let me first put the second condition first. And I'm actually glad, very glad for whoever asked me why can't we put a zero vector. Thank you very much, because that's kind of important to the first bullet point. But let's just talk about what intuitively we want angle preservation to be. So we basically want the difference between the argument r sub z, comma, gamma 2 prime at 0 minus the argument relative to r sub z, comma, gamma 1 prime 0. So you see, this is the difference between the tangent vectors to gamma 1 and gamma 2 at the point z. So angle preservation should mean that when I look at the argument, this time not at r sub z, but at r of fz. So I take some reference direction, and as I said, what that reference direction is not going to matter. But r sub fz now means you look at the mapping of z under f, and then at that point you take a reference direction, and you look at the curve that f maps us to. So you look at f composed with gamma 2, and you look at the dash of this at 0 minus, well, the argument. So I need to pick a reference direction. Its choice doesn't matter at f sub z. And then I have to look at the composition, f composed with gamma 1. And then I look at its dash at 0, right? Now, you see, I kind of made a big production about, well, this angle could be positive or negative if you consider counterclockwise measurement to be positive and clockwise measurement to be negative. But when we talk about angle preservation, we are not going to care about whether if you go from this vector gamma 1 prime to gamma 2 prime, if the sense of this traversal is clockwise, we are not necessarily in our definition going to insist that the sense of the traversal is preserved. Simply the difference between the angles is preserved, so I take the magnitude. Okay. Now, this might feel kind of arbitrary to you, but Doing this actually puts us in a situation of bringing linear algebra into the picture rigorously. And then we can even distinguish between what if you then additionally stipulate that the sense of the traversal in measuring the angle when you go from the tangent vector at gamma 1 to the tangent vector at gamma 2 counterclockwise is going to be. But the definition involves two conditions here. Now, do you see f composed with gamma 2 dash? You see, we know that by the chain rule, this dash by the chain rule is nothing but the total derivative of f at the point z acting on the tangent vector gamma 2 dash at 0. So why should the linear transformation, which is the total derivative of f at 0, return a non-zero vector when I apply it to gamma 2 prime at 0? It is possible that gamma 2 prime at 0 is in the kernel of this linear transformation, right? But when that happens, then if you get a 0 vector here, then as I said, you can't define the argument. To define the argument, you need non-zero vectors, because that is the situation when one is able to measure an angle from a reference direction to a vector. You can't talk about the angle of a 0 vector. So you see, to avoid that accident, for this to even make sense, we will require so I repeat again, this can be recomputed using the chain rule as the linear transformation df sub r at the point z acting on the vector gamma 2 dash. So you don't want any vector to vanish, which means that this must be invertible, right? So I can just say this is invertible, right? So in the literature, people write this as it lies in the space of matrices GL2R. Okay, so I pause here for a moment, and in fact, I want to ask you, do you have any questions on this point about this invertibility thing? Okay, so silence probably means people have got the point. Very good. So I'm now going to erase this picture because I need the board space, all the board space that I can liberate. So we have, at the end of the day, we have a definition for angle preservation. And I remind you that conformality means angle preservation at every point. So as someone had said right at the beginning, that measurement of angles requires one to endow the vector space with an inner product, right? And so that's now what we are going to do. So note that, so if angle bracket first entry, second entry denotes the usual inner product on R2, then what? F from omega to C. Remember, this is now we are talking about C1 smooth maps only. This is conformal. If and only if and only if, well, if and only if F preserves angles at every point Z, and then I told you 2 minutes ago what angle preservation means. So the first condition is, of course, the total derivative of F sub R at Z is in GL2 R for all Z, but in fact, let me make the second condition also and then say for all Z. So this is the first. Okay, maybe I'll do it for all Z in omega and now remember we talked about angles. So you have gamma 1 prime at 0, comma gamma 2 prime at 0. Now this alone does not give us the angle. You need to normalize. So you now look at the magnitude, gamma 1 prime at 0. So another reason why I want this quantity to be non-zero times gamma 2 prime at 0. So you see, when I normalize this, what I get is the cosine of the angle between these two vectors. But we have a problem. You see, this normalization tells us immediately one thing. It tells us that this quantity lies between -1 and +1, right? So you see, if you take the cosine inverse, you may not necessarily recover the angle going between the angle that is obtained if you make your traversal such that you go from the gamma 1 prime at 0 vector to the gamma 2 prime at 0 vector. That is because for cosine to be invertible, you have to restrict the cosine. So the principal branch of the cosine is the restriction to the interval 0 to 0 to pi. Why do we have to do that? Is because you see cosine is a symmetric function. So if I take a number between 0 and 1, then first of all, that number may be achieved. If it's achieved by an angle theta, it's also achieved by an angle negative theta. And then there is this, of course, or if it's achieved by the angle theta, it's also achieved by that angle theta plus 2 pi times an integer multiple. That's not so much relevant to me, but that the fact that there's an ambiguity of sign, SIG and sign, matters. And that because there is an ambiguity of sign, that is why on one of the sides of the equation that defines angle preservation, I choose to just go with the difference, which is a positive. So then what happens is that if I just want to go with the difference, then I can express this thing as on this side I'm going to have, well, first let's write F composed with gamma 1. Oh my. So I probably need to write down that second condition once more, because otherwise what I'm going to write next is not going to matter. Since I have talked in great detail about why we want this condition, I will not write this. The other reason why I want to rewrite the second condition is because I forgot to do something. The equation, so remember I wrote argument r sub z, comma, gamma 1 prime, gamma 2 prime at 0 minus argument at r sub z, comma, gamma 1 dash at 0, then this is equal to the difference. So I have here the argument. The key thing is I want r at f sub z over here. The reference direction should be a direction, a ray issuing at f sub z. And I have here f composed with gamma 2 dash at 0, right? So watch what I just wrote. So that's what we have over here. F composed with gamma 1 dash at 0. So this is coming from this expression. And then I have the absolute value. Now, everything that I said orally was correct, but you see, you would see a problem. When I put absolute values on this side, you know that this side is greater than or equal to 0. Whereas in the picture itself, we saw that this difference was negative, right? So when I said that we don't care about the traversal, we don't care about the sense of the angle as we measure the angle from gamma 1 prime to the vector gamma 2 prime at 0. Remember, in the picture, I took the trouble for that angle to be negative. So to say that we don't care about the traversal means that I should put absolute values over here. So I forgot to do that. So people, please make this change, okay? So I'm going to pause for 30 seconds for you to make the correction. I forgot to put absolute values on this other, on the LHS. So please correct your notes. Right. This is a correction. Okay. All right. And so, in fact, I had said that the reason we go with this definition and we don't bother about the orientation issue, the reason for that is that when I want to write this in the language of linear algebra, I have to look at inner products. But you see, when you compute an inner product and normalize and then try to deduce the angle between a pair of vectors, you have an ambiguity of sign, SIGN. And I want to be able to ignore that. So you have this, and then F compose with gamma 2 dash at 0. So these entries are coming simply from here. And I must also normalize. So this thing over, well, let's write it down. It takes a few seconds. So F compose with gamma 1 prime at 0, comma, F composed with gamma 2 prime at 0. So I have these normalizations as well, right? So I have this, and now I need to tell you for what I have these. So this is going to be for all gamma j. So these are going to be these nice curves. So gamma j goes from minus epsilon sub gamma j to epsilon sub gamma j. So you see, different gammas might have different domains of definition. That's okay. This should go to C, and this 0 must go to the points Z. So this is for all such gamma j's, such that not only is 0 going to Z, but also that gamma j dash at t is non-zero for all t. We want this to be true for j equal to 1 and j equal to 2, and also we want this to be true for all z in omega. So this is the linear algebraic transcription of conformality. Now let's look at a, yes.
Whether that is not equal or equal.
Oh, thank you. Not equal.
Sir, can you please explain this again for all gamma j from?
All gamma j from, this is the domain of the gamma j. So I am writing negative epsilon sub gamma j to plus epsilon sub gamma j to indicate that this domain will vary with the gamma j. We don't want to consider all of the gamma j's to have the same domain of definition. That's all this means. Do you get it?
Yes, sir.
Right. Okay. So this is if and only if.
Sir,
Yes. Your voice disappeared.
can you repeat why we need to? Hello.
Yeah.
Can you repeat why we need to normalize those vectors?
Otherwise, this is arbitrarily large, right? You remember this from your inner product theory, correct? That we recover the angle between a pair of vectors by taking the cos inverse. But to be able to take cos inverse, you can only take the cos inverse of something that lies between -1 and +1, right?
Okay, so for cos inverse thing, we need this.
Absolutely, exactly. For that and only that reason. But also, do you now see why I need to put absolute value signs over here? Because you see, cos inverse will return the principal branch of cosine inverse is the restriction, is the inverse function of the restriction of cosine on the interval closed interval 0 to pi. So if I want to infer the angle, doing cos inverse will give me an ambiguity of sign if I were going to insist on the orientation of the angle. So I only look at the differences instead, and angle preservation implies that the differences must be equal. Do you see that now?
Yes, sir.
Okay. So now proceeding further, do you see this is true for all, I stress, this is true for all gamma sub j's, any and every gamma sub j. So you see now, if you take your favorite vector, you take your favorite unit vector, you can find a curve C1 passing through the point Z, whose tangent vector is your favorite unit vector that you picked. If you now take another unit vector, then you can always find a second C1 smooth curve, call it C2, whose tangent vector is the second unit vector. So having said this, I can complete, having made this observation and having realized that I want this equality for any pair of smooth curves C1 and C2, I can completely eliminate this gamma and put in unit vectors over here. So this is if and only if you have the inner product between V1 and V2. This is going to be the inner product between V1 and V2. This is equal to, on this other side now, my V1 is some representative of the tangent vector of some C1. So instead, when I remove this gamma 1 from the picture, what I instead have, after all, when you do this computation, you know that this is going to be df sub r at the point z acting on the vector gamma 1 prime at 0. So I'm going to put in a V1 here, and then you'd have df sub r at z applied to the second vector V2. So I said that, so the reason there you don't see any normalization here is because I'm taking V1 and V2 to be unit vectors. So I have 15 more minutes, unit vectors. But there is no reason that these should be unit vectors. So unfortunately, the condition for conformality, it simplifies only slightly. Only slightly. So on, just because I took these guys to be unit vectors, unfortunately, I can't get away without a normalization on the RHS. It is what it is. So this is for all V1.
Sir,
Yes.
why that gamma j t cannot be 0?
What?
That gamma j of t cannot be 0 means.
What do you mean gamma j of? So we saw this right at the beginning, right? C1 and C2 are supposed to be smooth curves, which means they cannot have angles or they cannot have cusps. Because if we do that, you see, like if I have a curve like this, you see at this point, what is the tangent vector? There is no well-defined tangent vector, right? Do we go with this line or do we go with this line, right? There's an ambiguity. Do you see that?
Yeah.
So we want C1 and C2 to be smooth curves. And we know that there exists a well-defined tangent vector if and only if the total derivative of the map gamma 1 into R2 is of full rank, which is the same thing, is totally equivalent to the statement. Does that make things clear?
Okay.
So this is for all. So let's give an example where you have a corner. So let's look at, so this is like a nice example. Let's say I have a curve like this. And this is how I'm directing my curve. A parametrization for this, actually, let's see. No, let me give you an example where my example is C1. So let's look at the curve like this. Okay. So, and I want directed curves, remember? So this is the direction of traversal. Now, this is the curve given by gamma that takes t to t squared comma t cubed. So you see, this is totally a C1 smooth function, but there is no well-defined tangent vector over here, right? So I need a well-defined tangent vector, and the enemy to that is the total derivative of this map from R into R2 not having maximal rank. But that's just a very fancy way of saying in this simple case that gamma dash at 0 is equal to 0. So this is for, now I must say I stopped in the middle. This is for all gamma V1 and V2 in R2 such that they are unit vectors. So all V1 and V2, these are unit vectors. So I have achieved something in that this complicated thing has been replaced by the simple statement. And I must also say for all Z in omega, right? And so this, oh, and then of course I forgot. So, and also of course, as always, this double condition, this line is rewritten as this simpler expression. This, of course, comes along, and d sub fr z is in GL2R. And again here, of course, this has to be true for all Z omega. Okay. So I have, in fact, transcribed conformality in terms of, well, I would like to say linear algebra, but it's sort of linear algebra plus. It is in terms of the inner product. So I'm going to step aside and I am going to now, this is not very satisfactory, right? I would want to, if I can, be able to compute a little more, I'd like to be able to compute and get something more transparent out of it. So for that, please remember this star, okay? I am now going to go with this condition. So I am going to remove this intermediate if and only if, and retain and I'm going to retain this bottom half of the board, because this is the important condition that I need. So any other questions before we start doing some computations? Okay, so now I'm looking at an implication. So far, we were looking at if and only ifs. So this star, it's going to imply the following. So let us now take V1 and V2 to be those vectors, unit standard basis vectors, epsilon1 and epsilon2. So let's look at, you have d sub f r at z acting on epsilon1, comma d f sub r acting on epsilon 2. Now there's something very, very special about this pair of vectors, and that is not only are they unit vectors, but they are orthogonal. So you see this side becomes totally 0. So even though I do not have any information on the exact value of this, because this is 0, I know that the numerator of this has to be 0. So I don't have to worry about the normalization. So you have this, and let us now compute. We know the matrix entries of this guy, right? So the matrix entries are top left corner, del x u, then top right-hand corner is del y of u, etc., etc. So what we will get over here is when we compute this, we are going to get the vector del sub x u at z, comma, del sub x v at z. So this is one vector, and this vector is going to be del sub y of u at z, comma, del sub y at v of z. So you have this other vector, and this inner product is 0. So I have 5 more minutes. And I remind you that this has to be true for all z in omega. Okay, so let's simplify. This is a very simple inner product to do. So you get del x. So this is my shortcut basically of del x of u. So you get del x u, del y. Let's see, this is a del x u, del x v, del y u, del y v. So del x u, del y u plus del x v, del y v. This is 0 on omega. So this is the first numbered equation of the day. Now, I want to go further. So I will now erase this because I think you are getting the principle of what I am trying to do. The way I control for the problem of the normalization is by applying this to orthogonal vectors. So star also implies that del f r at z applied to, now I'm going to, instead of taking this vectors epsilon 1 and epsilon 2, I'm going to take the vector 1, comma 1, and then del f sub r at z applied to, I need something orthogonal to this. So I am going to go with, if you don't mind, minus 1, comma 1. This inner product is also going to be 0. And now this becomes kind of a messy computation, but when you do this, lots of cancellations occur because there's a negative term over here. And I'm just going to give you the final result. And the final result is, in fact, del x u, del y u plus del x v. So del x u, sorry, I'm writing the same thing. Del x u, del x v plus del y u, del y v is equal to 0 on omega. And I'll just give you the reasoning here. So this is just compute. Compute and simplify. And in the process of simplification, you will need you need to use this equation 1 in one of the steps of simplification. So this is our statement number 2. And I am 2 minutes to the end of time, but my strategy was, I want you to now show. So this is going to be the tutorial problem. Tutorial problem.
Angle preserved ಎಷ್ಟು conformal mapping angle preserve ಮಾಡ್ತೀವಿ ಅದನ್ನೇ prove ಮಾಡುದು ಅಂತ.
So was that a question? I think that is Savita. No? Okay. So tutorial problem is show from 1 and 2 that if f from omega into C, this is a C1 map, is an orientation preserving conformal map, then if this is an orientation preserving conformal map, then in fact F is holomorphic. So notice, if this is an orientation preserving conformal map, then F is holomorphic. But we can actually make a stronger statement. So this is your tutorial problem, but in fact, I have a theorem. And the theorem is, so this is sort of the hard half of the implication. So the theorem is, if omega is open in C, and what else? And F from omega, so omega is open in C. Then I will say F from omega, so F is of class C1 into C is an orientation preserving so I need to clear some space on the blackboard. Let me do that. So as always, this is going to continue. This mark of mine, you're probably familiar from yesterday. This means this part continues here. So this is an orientation preserving conformal map if and only if. Well, if and only if F is holomorphic. And now if F is holomorphic, we know that at each point F dash exists. And this is the part that F dash is not equal to 0, right? And so now the proof is, see, one direction is your tutorial problem. So the proof of, so the tutorial problem is basically the proof of this direction. So the proof of the opposite direction is just kind of trivial, because if you have F dash is not equal to 0, well, I mean, f dash from whatever we did yesterday, f dash at z not equal to 0 for all z in omega. Well, we saw yesterday that f dash not equal to 0 means that if you view this f as now an R linear transformation on R2, then that is a transformation that cannot map any non-zero vector to a zero vector, which is to say that df sub r at z is in GL2R. So that gives us the first condition in that statement. That was an if and only if statement star. So this is the one thing. And then the other thing is for this inner product property, for the other property, you see what happens is df sub r has a particularly simple form because of the Cauchy-Riemann equations. What we do is we use the Cauchy-Riemann condition. And what that does is it basically just trivializes the computation. And so what we have also achieved is we've completely classified, described completely all those C1 smooth conformal maps that happen to be orientation preserving. Okay, so I will stop right here. Of course, the hard part of the proof I haven't given, but that's a tutorial problem. So I'll stop here. I'll step aside so that people can stare at the blackboard if you're still in the process of taking notes. Also, any quick questions? Does anyone have any quick questions? No?
No, sir.
Okay. All right then. So please think, if you have any questions, we can take this up in the tutorial hour, which today is, yes. Who is this?
So in the Excel or in the,
go ahead.
so in the exercise, basically we need to show whether Cauchy-Riemann equation satisfies or not, right?
Exactly. Yes. Yes. Yeah. So you've actually given like the most important hint. Yes. Your final goal, you're absolutely right, because the part of the definition of conformality is that it has to be, F has to be, df sub r has to be invertible. So that part is sort of trivial. So the non-trivials, because that's a part of the definition already. So you are absolutely right that what we have to do is to show that F is holomorphic. So everyone knows over here that if a function satisfies the CR condition and is C1 smooth, then it is holomorphic. In fact, we actually don't even need this, but that's a more advanced result. So Arindam, you are absolutely right that the end goal is to show that the Cauchy-Riemann conditions are satisfied, but there is like a nice sort of linear algebra trick which is going to be needed. So it's not just all analysis. Okay, does that answer your question?
Yes, sir.
Yes, and I hope what Arindam said, so what he said is absolutely right. I have explained why this problem boils down to showing the Cauchy-Riemann conditions. So I hope everyone else present will take that as a hint. That is the goal you have to work towards. Okay, so I'm actually I've taken more than my fair share of time, even factoring in that I started a little bit late. I have gone beyond time. So we will have to end this. So Rajesh, do you have to end the recording first before we leave the meeting, or how does it work?
Yes.
Yeah.
Yes, we are stopping this.
Okay, great.